Good morning everybody. In this video we prove Dirichlet test. So this is a video lecture for the program BSc subject Mathematics semester 5 session 33. So let us start. Dirichlet's test. So this is the learning objective. These are the session outcomes. These are the prerequisites: bounded function, convergent, divergent functions, and infinite discontinuity. So let us start with Dirichlet's test. It states that let G is bounded and monotonic in the semi-open interval a to infinity, and let g of x tends to 0 when x tends to 0. Also let the integral from a to infinity f of x dx be bounded for all t greater than or equal to a. Then integration from a to infinity f of x g of x dx converges. So proof: the function g, which is monotonic in the semi-open interval a to t, is also integrable in the semi-open interval a to t for all t greater than or equal to a. Okay, so because g is monotonic in the interval a to t. So now applying the second mean value theorem, we have integration from t1 to t2 f of x g of x dx is equal to g of t1 integration from t1 to epsilon f of x dx plus g of t2 integration from epsilon to t2 f of x dx. Call this equation as 1. Now where this t1 and epsilon lies between a and t2, and t1 is less than or equal to epsilon. Now since integration from a to t f of x dx is bounded for all t greater than or equal to a, therefore there exists a number a such that integral from a to t f of x dx is less than or equal to capital A for all t greater than or equal to a. So this is equation 2. Therefore integral from absolute value of integration from t1 to epsilon f of x dx is equal to absolute value of integration from a to epsilon f of x dx minus integration from a to t1 f of x dx, okay, or which is less than or equal to absolute value of integration from a to epsilon f of x dx plus absolute value of integration from a to t1 f of x dx, again which is less than or equal to, this is also less than or equal to a plus this is also less than or equal to a because f of x is a bounded function. So therefore which is equal to 2a. Similarly, absolute value of epsilon to t2 f of x dx is also less than or equal to 2a. Applying the same technique as we applied here, okay, to this integral, we get this is also less than or equal to 2a. Now call this equation as 3. Now let nu be any positive number. Let n be any positive number. Now since f of x tends to 0, f of x tends to 0 as x tends to infinity, so therefore there exists a number k such that absolute value of f of x is less than n by 4a for all x greater than or equal to k. We now suppose that let t1 and t2 be such that t1 and t2 are less than or equal to k. So then absolute value of f of t1 is less than n by 4a and absolute value of f of t2 is less than n divided by 4a. Now call this equation as 5. Now from 1, 2, 3 and 5 we deduce that there exists a number k such that for all t1 and t2 less than or equal to k, absolute value of integration from t1 to t2 f of x g of x dx is less than or equal to absolute value of g of t1 into absolute value of integration from t1 to epsilon f of x dx plus absolute value of g of t2 into absolute value of integration from epsilon to t2 f of x dx. So this is by second mean value theorem. So which is less than or equal to n by 4a into 2a plus n by 4a into 2a, because this first integral is less than or equal to n by 4a, the second integral is also less than or equal to n by 4a. So right here, then this g of t1, this is a bounded function which is less than 2a, g of t2 is also bounded function which is less than 2a. So therefore by substituting those here, we get this is equal to n. So where n is a positive number arbitrarily assigned, so therefore which implies integration from a to infinity f of x into g of x dx converges at infinity. So this is the proof of the Dirichlet test. So these are the references. So with this I conclude this session. Thank you.